Alright, let's jump into these practice problems here. So we have our first one, which says the rate constant of the first order decomposition of cyclobutane at 500 degrees C is 9.2 times 10 to the negative third per second. How long will it take for 80% of a sample to decompose? Alright. If you would like to try this question out on your own, before I show you how to work through it, you can go ahead and pause the video now. The only thing I will tell you is that just remember that it is first order. So, and since we're talking about the integrated rate law, it's a pretty good bet that you will need to use this equation. The first order, oh, and I got the wrong sign there. The first order integrated rate law. So I had a negative there, that should be positive. Sorry about that. Alright, so if you want to try and work that out, you can go ahead and pause now. For the rest of you, which I would bet is most of you, let's go ahead and work through this. So there is at least one piece of information that's given to us in this question that is a bit of a red herring. That students tend to get caught up on as they see, oh, they told us it's at 500 degrees C, that must be important. No, it's not. Like, it's important in that the numbers would be different at a different temperature, but in terms of solving this problem, we're not going to use that anywhere. Instead, what we are going to do is we're going to take this, which is the rate constant, which we are told, because it says right here at the beginning, the rate constant for blah, 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 blah is 9.2 times 10 to the negative third per second. So that is our K. And then it also says that it wants us to figure out how long it will take for 80% of the sample to decompose. So it is asking us to find T. How much time? How long will it take? Now, it doesn't seem at first that it gives us everything we would need, because, you know, we're given K and we're trying to find T, but we don't know the concentrations. And the truth is, we don't need to know the concentrations because we know the relative concentrations. We know that we are trying to figure out how long it will take for 80% of the sample to decompose. So what that means is we can just pick some numbers. So if, for example, A naught is 1 molar, goodness, it does not want to let me do that. Okay. Then if 80% of it decomposes, A at time t would be 0.2. Hopefully that makes sense. Again, we're saying that 80% of it decomposes, so if we start with 1, that means we have 0.2 left. And you could do this with any numbers you want, as long as one was 80% or was 20% of what the other one was to start with. So as long as you've lost 80%. But 1 and 0.2 is just easy numbers to work with. So we have everything we need. So if we go ahead and plug in what we know, we're going to have the natural log of 0.2 is equal to negative 9.2 times 10 to the negative third per second times t plus the natural log of 1. Okay, so we have some math to do here. Now, some of you might know just off the top of your head, but the natural log of 1, that's 0. So this is just going to go away, essentially. And so really what we're going to have is the natural log of 0.2 divided by 9.2 times 10 to the negative third. Okay. do that math. That is going to give us 175 seconds. That's how long that would take. Okay. So moving on to the next one here. This one is going to be a little bit more in depth because we actually have to make a graph for this one. So this says consider the equation for the decomposition of SO2Cl2. The concentration of SO2Cl2, of SO2Cl is monitored. Actually, that's a typo there. It should say Cl2 because that is what we're monitoring. At a fixed temperature as a function of time during the decomposition reaction, and the following data were tabulated. Show that the reaction is first order and determine the rate constant for the reaction. So if you remember for first order reactions, if we plot this data using this equation, we should get a straight line if it's first order. So that's kind of our first step here, showing that the reaction is first order. We're going to do that by plotting the data as if it was first order, and then if we get a straight line, that confirms then that it is first order. And then the second part, determining the rate constant. Goodness, I don't know why it doesn't like me writing m's. It gets really upset when I write m's. That is the slope. So when we get our graph, we're going to take the slope of that graph, and that is our rate constant. Well, technically, the negative of the slope will be our k. But to do that, I'm going to go ahead and discard that, and we'll pick it up there when we go back. So I have the data right here. So this is the data, same data from that question. So this was time, and this was concentration. And what I'm going to do is I need to take the natural log of all of this data. Because remember the equation, let me see, well, let me write on this. Oh, it will. Cool, I didn't know it would let me do that. So if you remember our equation here, we need to plot the natural log of the concentration versus time. So I already have the time, that's taken care of. I need the natural log of the concentration. Now I could go through and type every single one of those concentrations into my calculator and get the natural log, and that would be perfectly fine and acceptable, and I could type them all in. I'm going to do it easier though. I'm going to do it a much easier way. I'm going to have Excel do that for me. So the way that you can get Excel to do math for you, and again, if you've been working on the Crystal Violet lab, you should have already done this. But just in case you have not yet started on that, if you hit the equal sign inside the cell, that tells Excel that we're about to do math. So you can say, I want this cell to equal the natural log, so that is ln. I'm going to open parentheses, the number from this cell. So I click on that cell and it says, okay, I'm going to take the number from C2. I'm going to close the parentheses and then enter. So this is the natural log of the number in C2. Now if you're thinking, well, that was not terribly efficient, I can do it faster on my calculator. Oh really? Haha. That was much faster than doing it on your calculator. If you didn't catch what I did there, if you see this little square here right in the bottom right corner of the cell, if you take that, and you can either click and drag, that will also work, click and drag or double click on that, and it will take the equation that you have in this cell, and it will just continue it down until it runs out of data to work with. So it takes the very next cell down, and it does the exact same thing to that cell that it did to this one. Now it does not take C2. If you notice, the C value, the cell that it is referencing, changes. It's because when it does the exact same thing, it doesn't say I'm going to take the same cell. It says I'm going to take the cell that is oriented to this cell in the same way that the previous one was. So here it reads it as this cell is equal to the natural log of the cell next to it. And so for all the rest of them, it just does that same thing. It just says I'm going to take the cell next to it, the cell one to the left, essentially. And so if I had selected this cell over here, it would instead say, okay, take the natural log of the number 2 cells to the left. So that is much faster than typing it into your calculator. So now that we have natural log of our concentration, we can make our plot. And so we're going to do that by taking, let's see, I believe it's going to put X, Y. I think that's the way Excel always does it, is it picks the column on the left to be X and the column on the right to be Y. I think that's the way it does it automatically. So what I did right there was I clicked and dragged to select those, and then I held Control and then clicked and dragged to select the second column. If you just click and drag twice, it'll only let you do one column at a time. But if you hold down Control, it will let you select more cells to be included. So then we're going to go to Insert. Right here under Charts, we have Scatter, which is what we want. That looks good to me. Nice negative slope, which is what I was expecting. So that means that it picked our axes correctly. We wanted the natural log, or actually no, it didn't pick them correctly, did it? But it still ended up with a negative slope. Because we wanted, oh no, it did. Yeah, it did. Never mind, it did. We wanted time to be X and natural log of concentration to be Y, and that is what we have. Just throw me off a little bit because it's in the negative quadrant here, but it did pick it correctly. Okay, so it is X, Y. That is normally how Excel does it. If you just pick two columns, it normally puts the one on the left as the X and the one on the right as the Y. If you don't have your data set up correctly to where that would work, and you prefer not to shift them around, there is a way to change that. If you go in here and you do select data, and you go to the series and you edit it, and you select the X that you want, and then select the Y ones that you want, like you can do it that way. Usually I find it easier just to make sure that I have the X on the left and Y on the right. Now we need to put in a line just to prove that it is straight, and also to get the slope. So what I did right there was I right-clicked on one of the data points. So if you right-click on a data point, and there's already a trend line there, let me delete it real quick. So if you right-click on one of the data points, one of the options will be Add Trend Line. So you click on that, and then usually you'll want to select these bottom two. You don't always need the r-squared value. The r-squared value is just a statistical function describing how close the data points are to your trend line. And the closer to 1, the better. The fact that this data is exactly 1 tells you that this data is fake. This is canned data. Somebody made it up. But regardless, this shows us that we do indeed have a first order reaction, and it also tells us that K for this reaction is 0.0003. And it would be per second, because that is the slope there. Let me make that a little bit bigger so you can see it a little bit easier. So the slope is negative 0.0003, and since we have that negative there in the equation, it cancels it out. So it's just positive 0.0003. All right. So that was this question. Let's move on to the next one here. So this question asks, the reaction of butadiene gas with itself produces C8H12 gas as follows. The reaction is second order with a rate constant equal to 5.76 times 10 to the negative 2, 1 over moles minutes. Again, I'm kind of confused as to why they insist on showing the unit of molar separated out. But it is 1 over molar minutes under certain conditions. If the initial concentration of butadiene is 0.2 molar, what is the concentration remaining after 10 minutes? So we are asked to find concentration at time t, that time being 10 minutes. And we're given the initial concentration of 0.2. So this one is pretty straightforward. If you remember the equation from a few minutes ago, so again, this was back here, the integrated second order rate law. We are asked to find that, and we're given everything else, essentially. Everything else in the equation we are just given. Really, all we have to realize, or all we have to do, is realize that we are in fact given all of those things. So what we can do is we can just plug and chug and have a little bit of algebra to do at the end. So 1 over the concentration at time t is equal to 5.76 times 10 to the negative 2, 1 over molar minutes, times time, which is 10 minutes, plus 1 over 0.2 molar. Alright, so we have some algebra to do here. If we go ahead and multiply these two together, 5.76 times 10 to the negative 2 times 10, that'll give us 0.576, 1 over molar. Let's see, we still have plus 1 over 0.2 molar here. So, and believe it or not, those units actually work out, as you can see there, because this is 1 over molar and that is 1 over molar as well. So we can actually just take the 0.576 and add to that 1 over 0.2. And that gives us, let me write it down here, kind of running out of space there, 1 over concentration at time t is equal to 5.576 1 over molar, which might seem like, oh, there we go, we got the concentration, 5.576. But that is not the concentration. That is the reciprocal of the concentration. Because notice here, it's not equal to the concentration, it's equal to 1 over the concentration. So we need to take the reciprocal of that number which, if you remember, is just to take 1 over that number. We're essentially just going to flip the whole equation. So we're going to end up with concentration at time t is equal to 1 divided by 5.576, which is 0.179, we'll say. And that is, I know I lost my unit there, but that should be molar, and is molar. And that number makes a certain amount of sense. The rate constant is fairly small, so we don't expect a huge change in the concentration, and the concentration decreased. So that number makes sense. Okay, last one here in this video. This says, consider the equation for the decomposition of NO2. The concentration of NO2 is monitored at a fixed temperature as a function of time during the decomposition reaction, and the data tabulated in the margin at the right. I know there's no margin at the right for you there. I have it in an Excel sheet we'll look at in just a second. Show by graphical analysis that the reaction is not first order and that it is second order, and determine the rate constant. So this is going to be very, very similar to what we did just a minute ago, only now we are going to have two different graphs. We're going to have a first order graph with the natural log of the concentration, and we're going to have a second order graph with 1 over the concentration. So we'll do the first order one first, just like we did before. We're going to say this cell is equal to the natural log of that cell. And then for the second order, we're going to say this cell is equal to 1 divided by that cell. So then once again, we get those to fill in for us. So then to make the two plots, do first order first, select time and the natural log. So I'm going to go ahead and change this chart title so I can keep track of what's what. And I think I'm going to go ahead and format that axis as well, because it's kind of hard to see what's going on. I'm going to tell it to move the bounds to where 0 is not the bound. I'm going to say -4. Yeah, it's a little bit easier to see there. Okay, so that is first order. The second order, same deal. Select my data, insert an XY scatter. So this is second order. I don't need to adjust the scale on this one. It's fairly easy to see. And so I'm going to go ahead and put a trend line on both of these, and make it where you can see that a little easier. Alright. And if you're thinking to yourself, my goodness, he just did 2 graphs and put all that math in there and made the trend line and everything, and it took like 2 minutes and it takes me forever. It's like, I've literally done this dozens and dozens and dozens of times. I could practically do this in my sleep. So don't feel bad if it takes you 5 minutes to do this, what took me just a few seconds. It comes with practice. So if we look at these 2 graphs here, the first order one, the R squared value doesn't really seem all that bad. It's pretty close to 1, but when compared to this one, you can see that this one is straighter. This is actually, again, another example of fake data. But another way that you can tell that this is not a straight graph here is that the data points that make up the line, the first data points are above the trend line, the data points in the middle are below, and the data points at the end are above again. So you can tell the whole line is curving around that trend line. When you see that, it's a dead giveaway that your data is not actually straight, that it is actually, it has a curve to it, even if it is kind of hard to see sometimes. So, we do indeed have second order data, and just like before, the rate constant is just going to be the slope. Only now the units should be 1 over molar seconds, because that is always the unit for second order rate constants. All right. So that was a whole bunch of examples there, but hopefully you find those useful, both for the homework as well as for that lab if you are working on that right now. If you have any questions, let me know, and I will see you in the next video where we will talk about half-lives.